my pleasure to introduce Sayan, who will be talking to us on stochastic topology, statistical inference. So thanks a lot, Sayan. Please go ahead.
Okay, so I guess for everyone up, and I'm giving a talk into the laptop, but I'll try. And feel free to interrupt at any point. So let me say a few things first of all. I guess just as a background, I'm going to, as I go through these slides, what I'm trying to do is give a feeling for ideas and things people are trying, and hopefully to motivate you to try other things and think about other problems. All things I'll talk about, I guess, are a bit more of work that I've done, but the only reason why is because it's easy to talk about that, and a lot of these ideas, really, many others have been thinking about working on them as well. So, as a concrete example, I have a colleague who looks at bones. So there's a problem in morphology, and we want to measure distances between bones, and I'll come back to that. But this is an example of where ideas from topology have been practically useful in doing, and there are other instances of this, similar problems in archaeology and also in shape modeling. We'll come back to that. Another problem that I've worked on, where I think there's a lot of utility in thinking about the ideas from topological perspective, is the following. I have collections of networks. The blue one, the green one, looking at it to the left, is a behavioral network of how some baboons groom each other, how often they groom each other. And the right is not the same baboons, but from the same troop. So there's a subset of that are overlapping, how much microbiomes are similar. So how much the species content, the bacterial species content in these baboons are similar. And what we want to ask is how much does variation in a network explain variation in another one? And you have to do this in a coordinated way, in a sense. So again, topological methods are very well suited. So I think from a statistical perspective, a classic idea in statistics has been exploratory data analysis, where before we try to apply formal statistical models, you want to summarize the main ideas or characteristics of the data, and then from that you can later on go to more formal statistical hypothesis testing, so on and so forth. And this idea was really highly developed by John Tukey, who actually got in topology, but be a prominent statistician. So one of the things that people, I think, early on have observed is topological data analysis does do a very good job in exploratory data analysis. And I'll give a few examples of that. But one of the things I also want to kind of highlight and stress is it also can serve, and there are ways of using for formal statistical reasoning, and I'll get back to that. I'd say one of the examples of people looking at topological data analysis is something called a Wells tube formula, which some here in the audience are very familiar with. And so this is a problem that was given by Harold Huttling. He visited, I believe it was Princeton, and Huttling was a very prominent statistician, and a lot of things like various types of principal components analysis and things like that were things that he worked on. So the problem that he gave here was, if I have a Euclidean space, I want to basically thicken the space slightly and ask what the volume is around it. So if you were to think of it in a way, while work this out, you can think of this as a T expansion to estimate the volume of a tube of small radius around d-dimensional submanifold in space. What the formulation of this is, if you have an oriented closed surface for epsilon, of the epsilon neighborhood can be given by the function of the area and the Euler characteristic. Now, it's interesting that the Euler characteristic enters here, and later on we will talk about other types of topological summaries of data. Here our data is a closed surface that help us characterize or model data. So again, to highlight this idea of topological summaries. Be fun. I think, frankly, of topology or the idea of coarse geometry, people have really thought about kind of Platonic ideals, objects that really highlighted concepts, right? And I think one of the things that's interesting in going towards thinking about stochastic topology and inference in topology is that it's not exactly the ideals we're interested often, it's variation. We're very much interested in how do topological summaries vary for different types of objects, and then I'll that again. So Betty numbers are very standard. I think everyone here knows what Betty numbers are. For example, I have the number of components, 1 holes, 2 holes, so on and so forth. Okay. The Euler characteristic again is another one that's of interest. You think about the Euler characteristic as an alternating sum of the number of the Betty numbers. If you have a simplicial complex in R3, these are just the vertices minus the edges plus the faces. And we'll back to that. And again, just pictures of how these are invariants. One idea we're going to come back to are the idea of critical points. They'll come up very naturally in Morse theory. And I'm just going to very quickly go through persistent homology, just if so the idea here is I have here, and we're going to basically think about a Morse filtration on it. So I'm going to slide up a new one time, new happens on the x-axis, right, in the sublevel set. I put down a dot, and so a new one come in, so on and so forth, and that one's going to disappear, so things merge, and so it dies, and you can basically construct something like this, which is called a persistent diagram. And the idea behind persistent homology is how long does homology group persist, basically. And again, just simplicial complexes have independent points, there's a non-empty subset of it. These are oriented, which are just even permutations. Define a boundary map. If I have 2 vertices, the boundary map is just going to be 2 edges. For the face, takes it apart into the for the edges, they become 2 vertices. For the face, it gets taken apart the edges. And that's the idea of a chain. If you have a simplicial complex of a particular dimension, what chain is really are mapping it from higher dimensions to lower dimensions via a boundary map. And thinking about the boundary map is an altering sum, just removing one of the vertices, okay? So and this is a picture. If I have complex and they're oriented and I have them labeled, if I apply a boundary map to them, you get go from left to the right. And again, to you. Now, one of the points and one of the ideas why this is often algebra topology, you say something about the Betty numbers, and you can say something about the homology groups using algebra. And make a point here. The key idea in when persistent in homology, and the reason why it became very powerful was the ideas by Gunnar Carlson and Afra Zamordian and Herbert Edelsbrunner, where they realized that all of these can be written and they be done in terms of linear algebra. And one of that I think would be very interesting is, and it'd be interesting to highlight, since these are all linear algebraic objects, and we'll talk about this, we're inferring these from data. You have data, you construct a simplicial complex, and then you turn it into this linear algebra problem that you solve. And it would be very interesting to ask, can one do some type of perturbation analysis of that matrix itself? And is there an intelligent or interesting way of doing randomization on this linear algebraic object itself, on this matrix? And that's one thing that we haven't explored a lot that I think is really interesting. So I'll just stop and make some kind of asides as we go on through this, and please feel free to ask questions as we go. Another example of this, one area where I think we haven't done people have been doing work, and the work here is really Konstantin Maikow's group, I think, has done a lot of really interesting work in thinking about how topological data analysis can affect dynamical systems. And this version, what we're going to see, something that John Hare and Jose Pereira have I've been thinking about is you can take a time series here, take a window of it, and run a sliding window through, and this will give you a bunch of points. And basically, you can say something about limit cycles in this series via the geometry or really the topology of these points. And so you can construct a filtration. Then again, you get this idea of persistence. Okay. Now, one of the things that I think we haven't done yet, and I think could be very interesting, is asking the question of, can we not just study parameters of a time series from observations, but can we say something about the generation process? Is there some way of group actions that one can infer from the time series? Again, I think this is an open problem, which is interesting. Just look at some history of this. Like I said before, there's work done in computer vision, then combinatorics, the idea of discrete Morse theory from Robin Foreman and going on. In statistics and probability, there has been a lot of work on people looking at MRI and, Robert Adler and others who've thought about random Gaussian fields, and these relate to the Euler characteristic, and I'll come back to that later on. Okay, so what people have been starting to ask more and more and think more and more about are what are statistical properties of persistence diagrams. But I think we generalize that a little bit. And the real question is, what are statistical properties of logical summaries of data, or statistical properties of coarse scale geometries of data? Because in essence, in the inference problem, that's what we're asking about. So why we want to look at summaries? Let's say if you have a torus and a double torus. So the classical statistical perspective on this idea, on this problem would be, I view data, which are point clouds, and I give m point clouds from a torus. So I take the torus, I sample, let's say, L points from it m times, and this gives me data sets, okay? And I'm saying they're just drawn all the same way, and they're drawn from a density. Now, the fundamental idea in a lot of statistics is what's called using likelihood, right? And there is some likelihood in that there is some parameterization of density that's being drawn from the torus, and objective is to infer or figure out what those parameters are. Okay? That's what we want to do. Now, similarly, let's say we have another set of data. These are endpoints, and they're drawn from the double torus. Now, another point, it's drawn from the torus or the double torus, I'll tell you which it is. And I ask you, well, which one is it? Which one did it come from? Now, if I can write down a model, right? I have two of them. I have F, Z, set hat 1. That's my model for a new point. Give parameter estimate theta 1. Theta 1, again, is my parameter estimate for the single torus. And literally, I'd have one for the double torus, which would be theta hat 2. A way of basically give probability of which object it came from. And this is just using what's called Bayes' rule, or just it's a property of conditional probability. Now, to do this, I have to be able to write down a reasonable model and infer it. If you want a likelihood model on the torus or the double torus that actually exactly generates the data, it's a little bit complicated. It's not as simple as it could be. A much simpler model is just computing number of holes, right? So if my data, instead of were actually a sample, it was a number of holes, which is a summary, right? Which you can think of here as a Betty number. We basically do the same thing, except we now just need to model or put a distribution on Betty numbers, which is much easier because these are integers, and we know how to do that very easily. So this is the idea of how you do inference with summary statistics. Now, clearly, in this, we've lost information as gone from a model on the data to the model on the summary statistics. And we'll ask questions, for example, ours is when we don't lose information. Ours is where we want to lose information. What information do we want to lose? So again, the inference problem on the data may be hard. We'll come and I'll show you this again. The inference problem on the data may not be robust. We may not be interested in capturing the exact geometry. We want to be able to be robust to certain perturbations or invariants, right? And one example is we use persistence homology as summaries. Okay. Now, if you're, this is on the far left, we have the function. In the middle, what's a barcode representation, and on the right, we have a persistence diagram. The bar and the persistence diagram are in a sense the same. They're just two different representations of a summary. And one can start asking a very simple question. Can you do averages of these things, right? Can you start doing what we do with, measurements of, lines, right? What we do with scalar random variables in this setting. And again, the argument for doing that is if you believe that this is summary, then it should have some statistical properties. It should be a random variable. We should be able to compute invariance of it, so on and so forth. Okay. Now, the thing when you want to think about something a random variable, you have to worry about the probability space it lives on. And so the way we do this is we first start with a metric, so a diagram. There's a way of measuring distances between them. There are actually a variety of them. One is called the L2 Wasserstein metric, which is if I have diagram X and Y, let's say the red and the blue, I'm basically looking for a bijection that matches all the points in the red to the points in the blue, and then the L2 distance between them. Points for points that cannot be mapped, they get mapped to the diagonal. So basically it. You can have any LP Wasserstein metric. There are other bottleneck metrics and so on and so forth. Okay. So now one of the things that you show, and this is just another form of a thing that has been proven earlier by Cohen-Steiner and Herbert and John and others. The point is that if I have functions f and g that are Lipschitz functions, and if I control the L infinity norm on the functions, I control the distance between the diagrams. So one argument is that this may be a reasonable summary statistic because it's stable. Perturbations on your actual functions will be small, will cause not horrible perturbations with respect to distance between diagrams. So one way of, again, defining a persistence diagram, so multiple points are 2 above the diagonal, and the diagonal has infinite multiplicity. So persistence diagram is all the diagrams that are finite distance away from the null diagram, which is a diagram with only a diagonal. Now I have a metric and now I have a space. Now the kind of classic way what you learn when you learn, probability with measure is that if something is a Polish space, you can start doing probability theory with it. And for something to be a Polish space, it needs to be complete and separable, and this happens to be true. So that's good. Things that you start asking is, okay, this is a probability space. How can I start reasoning with it, or I start working with it? And one of the things that I'd also like to say is, right now I'm only saying this for a summary, which is this persistence diagram, but you can for many other summaries. I think for those of you who've looked at Peter Bubnick's work on persistent diagrams, that's a summary which I think is extremely powerful and has lots of very nice properties. And I think one of the things is that may have some worth is we always have to look at the particular types of summaries that we've used in the past. There are probably many other summaries out there, some of which are of computational benefit, some of which have maybe benefits. And again, the argument is, if at the end of the day what you want to do is solve a statistical problem, maybe we can relax some of the cleaner algebraic structure that we have for the summaries that we work with now. So I'm starting with a point cloud. These are endpoints drawn from some distribution. So this is a starting point in most of statistics. We think of this as a likelihood. So for now, just think of it this way. Z product space. So saying is that my points x1, xn, I told you they're drawn IID, and my sigma algebra is against a product space, and my distribution is again a product space. So persistence diagram is just a map from the data onto the space of diagrams. Under weak conditions, this is measurable. And the point here is this is measure on diagram space. So if I have a probability measure, right, and let's say even a probability density function in my original space, in my data space, which is what I would need for a likelihood, this is going to induce a measure on diagrams. So that means that induces a measure on summaries. Now, this later on, but sometimes it's really hard to write down the density in space of in the actual original space in the objects. So an example of this is the bones, meshes on bones. We'll come back to that. But it might be easier to work and put down distribution density on the summary. Okay. Thing about here, this is now think of joint and conditional measures of both the data and the parameter on the diagram space and the parameter space. And also you can think of theta conditioned on the diagram. There's an idea in statistics for a while. So ways people think of doing statistics is you have data, think of it as a point cloud. There's data generating process, okay? And process may have a finite number of parameters, like a univariate normal, or it may have an infinite number of parameters. For example, some types of stochastic processes or random curves, okay? Or for example, something like Brownian motion. Now, the idea is one could, in theory, write down something like what's called a likelihood, which is the model for how this data is being generated. Maybe instead of using the likelihood, we get something which is a bit more coarse, which is a distribution on these summaries. This idea is something called a substitution likelihood, and it goes back to Jeffries, who knows a lot about various types of inferences, okay? We can come back to this. What invariances on the data is a persistence diagram a sufficient statistic? Meaning, are there particular constructions where it's not a summary, it's a sufficient statistic, and that there's no data information lost? Now, once we have, with thinking about persistence diagrams as a summary, is that it is a metric space, but it's a very painful metric space to work in. Something called an Alexandrov space bounded from below. So here I'm just defining what the G6 in this space look like. And you can prove that this is a non-negative curved Alexandrov space. The problem with this is geodesics are not unique. So if you just of how we often think about metric spaces is in terms of comparison triangles, right? These are not unique, so there's problems. And so you can define Frechet means and Frechet variances here, but the Frechet mean isn't going to be a single mean, it's going to be a collection of means. And I'll say again, what's one of the approaches to get around this has been what Peter Bubnik has done, which is work in nicer space, something that's Banach. But define a Frechet expectation. You can say that if your probability measure behaves reasonably in finite second moments, or then you will have the means not it exists. And again, the same with bounded conditions. And then you can start asking questions. Do we have concentration? Do we have a law of large numbers? So if I do NMs, I can define an empirical Frechet mean, and that's in this slide. And does this empirical Frechet mean converge to the extent or the true mean? And so this is in random field. And you can do is you can get from Gaussian random field. And this is just showing you how it looks as you average them, just to show you we can average them. And the next few slides, all I'm saying is that there's a law of large numbers for this. The formula above is the set of expected means, the formula is the set of empirical means, and under certain conditions, we can prove concentration, but our conditions are pretty restrictive, and practically, this theorem that we have right now is practically not very useful. And again, the difficulty is because you have you lack the non-uniqueness. There have been ways of people that have been working to get around it, and there have been ways of people have been thinking about modeling these diagrams. There have been many efforts of modeling them as point processes is one way, which is very natural because you can think of these as point processes. Another way of modeling them, if people have been thinking of something that's called Dirichlet distribution or Dirichlet process. The idea there is, since you just don't have a single mean, it's not unique, you can think of a probability measure over means. And that's been another approach, okay? What I do want to say, I think is interesting, is if you look at a diagram, there's been a lot of ideas and statements that, well, things near diagonal leave our noise. And that may be true, but it also may not be true. I think the point is that things in the diagram, I will agree, we're much more uncertain of. That's certain. But in noise, and there are actually cases where things are well explained by looking at a large collection of points that are near the diagram. And so this is looking at particular brain images, and the arteries are twisting very tightly. And this goes back to think about defining noise. And in Philly, we've always said, well, it's a threshold or cutoff around the diagram. But if there's a model for your data, right, and a notion of something that's going to be a likelihood or a generating model, then you actually have to do a little bit more. You have to work a little bit harder to actually formally model what these diagrams should look like. And I think there's a lot of interesting work that can be done there. So I have that comment with that. There's another way of thinking about this, another way of looking at this, and this is something that I didn't get to hear all of John's talk. He spoke, I think, was it last week or a few weeks ago? But what John was talking about, how one can do machine learning using topological summaries, and I think there's a lot to be done there. And the idea there is a lot of machine learning, or a large class of machine learning methods depend on something called they're called kernel methods. And the essence of them is that you have a function, you have data. From the data you want to estimate a function, and that value of that function might be a label. It may be a real value in terms of modeling height, or modeling body mass index, whatever have you. And the idea is that a function is a linear function, Ci, of kernel function around some data points. This kernel need only be positive definite, right? A sick example of this is these kernel functions, a little Gaussian bumps, and trying to do function fitting, right? I have observed data. We're going to put a Gaussian on each of our observed data, and we can give it a weight, and our function is a linear combination of these weights. Now, gave you two. Now, you can do this. If you think of your space as a space of diagrams, if you have some metric, some function of the metric which is monotonically decreasing, that will give you a positive definite kernel function. And so you can start doing learning using these summaries. And there's been some work done that. I know Gunner's done some stuff, and then John and Paul have done some stuff, and other people are trying to develop this idea. And like one very basic question is, we know about function estimation on standard spaces, but we know what it looks like on these diagram spaces. It's kind of an openish question as to the geometry of these summaries or these diagrams change how we do function estimation. And I think that's again is pretty open, and thinking about how to adapt the variety of machine learning kernel-based algorithms out there to this type of setting is also something that I think a lot of work can be done in. So again, that's something I think is pretty open. Now, some work that I'd been doing with Catherine and Turner, and now we're extending some of it with others, specifically Washington Yale. But the question is, are these summaries are actually sufficient in that they characterize everything? I'll motivate this by an example. I have a colleague in evolutionary anthropology who studies bones, and he wants to study them for basically evolutionary analysis. He wants to look at distances between bones in the type of tree to kind of idea of, at least at the phenotypic level of these bones, what would have been some notion of speciation, right? And the way it's initially done, this is collaborative work with Ingrid is they use some geometric ideas to measure similarity in that, in the case here, these are teeth, down a set of landmarks, and you ask what's the variational cost, a little ball around each landmark, and ask what variational cost to transform one of these little patches into another one, and then you integrate over patches, right? So this is, using ideas from conformal geometry to try to measure the distance. And it's very pretty work. I highly recommend if anyone's interested in at it. A very, very kind of classic idea in statistics of using landmarks and called shape statistics. So a very, method in morphology and other areas is you take an object, you set landmarks, you landmark, you look at the tangent plane, and then you collect those. You collect these M tangent planes, and you can think of that as matrix, and that's in essence your object. Okay, it's your summary of the object, and then distances are basically just distances between these matrices, modulo, rotations, translations, and scaling. It's called shape space. In other words, Procrustes distance, that's what it is. Now, this is very natural going back, because if you were at a museum or elsewhere, the objects were actually measured was you look at points, say these are the important points, and those are your landmark or reference points, and other points that you get another object. You again look at these landmark reference points, decide what they are, and these distances. Going forward, this is changing in that in museums and other places, people are doing CT scans, so we're actually getting full meshes. So you can do a lot more. Now the question is, what happens when these shapes are not isomorphic? In this case, they are. These are two heel bones. They can even be the same. They are isomorphic, but what happens if they're not? What happens if, for example, you have broken claw tips? What can you do? And I'll talk a little bit about this. And one idea is you can use integral geometry. So there's these ideas, Hadwiger integrals, Minkowski functionals, and the basic idea of Euler integration, of which the radon transform is a particular common example. And if one wants to look at more examples of these, I think Matthew Wright's thesis is very nice and contains a lot of these examples. And the radon transform is used very often to imaging technologies, right? So go use this idea. So there's this idea of a height function. And we got this from a paper by Yusu Wang, where they're thinking about and trying to model protein structure. With a bone, I take a plane, and then I'm going to take the perpendicular to the plane, and I'm going to basically run it through the bone, just like that Morse idea, the one-dimensional Morse function idea. And it's from different directions. And this is all we have, something called a persistent topology transform, spatial complex in RD. I take the directions of unit vector, and I'm going to x sub k m v is changed into a topology. So if I have an index r, the letter r is the sublevel set as I go in along there to the plane dimension r, and one can define the transform as a map of the persistent homology. Take the mesh of these directions on the sphere and then map it into a bunch of diagrams, and do this for various directions and for various dimensions. So x0 is 0th dimension, 1st dimension, so on and so forth. Okay, so once you have this, you actually look at the space of finite social complexes of RD. I can define distance between two surfaces using this, and the surfaces are aligned. Just look the between the two distance diagrams coming from a particular direction or a particular dimension, integrate that across all directions, and sum it over all dimensions. Now, obviously, you can't do this integral over all directions, so you basically do a discretized set, and you do that as a sum. Now, you can do the same thing without a persistent diagram. You can do it in the Euler characteristic. So similarly, before we can compute the Euler characteristic of the sublevel sets, so this gives the Euler characteristic curve. Just this is a mesh of the heart of an embryo. Just looking in one direction, that's its image, And the first image on the right is the Euler characteristic, and then you can think about basically integrating that and zero meaning it. And we'll get back to why we did in a second. Now, the idea of a statistic, and the idea of a sufficient statistic is I have X, it's coming from some distribution, and a sufficient statistic is, well, it's a statistic I can compute from the data, so it's a summary. So in a joint distribution on that summary and the parameters. And telling you is I could have thrown away the parameters and I would have lost no information. Okay, that's the idea of a sufficient statistic. So a classic example is if I have a univariate normal, right, I can just compute the sample mean and the sample variance, and I will have lost no information. Okay, so we can just the topology transform is injective. Now, this statement, the following sufficiency statement that I'm going to make, is a little interesting, and let me tell you why. So if we have a subspace of shapes, let's say in 2 or 3, and these linear simplicial complexes with n vertices, density function over the space with and of our mesh is in a n, meaning that it's again meshes of dimension k with n points. The homology transform is a sufficient statistic. Now, we're more used to looking at statistics. This is a little odd because things are usually done is first tell you the distribution on the meshes on your original space. And we say this family of distributions, this transformation, is a sufficient statistic. Now, interesting here, could be borderline shady, is I haven't told you what the distribution is or the original set of shapes. Now, the reason is it's very hard to think about putting down distributions on meshes with n points. What are ones, what are ways of thinking about it, how to do that cleanly. So that's one of the reasons we didn't do this. That being said, our statement here is not correct because there's a way of proving this idea using Nicodim derivatives and dominating measures, and I won't go into that. It's correct, but it's a little bit tricky because it doesn't make explicit what family of the distributions on the original shapes were. Say for the Euler characteristic transform, there's a little more you can do with the Euler characteristic transform, which is something that we're working on right now, which I think has a lot of potential. So, like I said, if you think about the Euler characteristic transform, what is it? The way it's a collection of curves, right? For each direction, you get a curve. Now, one of the reasons people look at things like sufficient statistics is typically they satisfy something called an exponential family, which just means the density that's generating the data can be written in the first equation we have. Just think that depends on the parameters, something depends on the data, and something depends on the exponential of the inner product of the data, parameter with the sufficient statistic. Write down the likelihood for surfaces meshes if you had an exponential family in terms of the bottom formula. Now, integrate this curve, okay, smooth curves, and now that this admits an exponential family. If these k-smooth curves, okay, each of them, and we discretize them, now is discretized in terms of t points, right? This gives me a k by t matrix, and there's a quick way of modeling that. We know how to put distributions on matrices like these, and one way of doing it is something called a matrix variate normal, the analog of the multivariate normal. The multivariate normal models vectors models matrices. So if my matrix is F, I have a parameter which models covariances between curves, and V that models covariances between points in a curve. So we just started doing this, but one of the things we're starting to do is, can we use this matrix variate normal approach to do kind of very standard likelihood modeling on these surfaces and shapes?
Cheyenne, what is K?
Is a number, capital K is a number of directions. Okay, capital T is for direction you get a curve. It's the number of points I'm discretizing the curve at. Okay? Okay. So starting to see, which is really interesting, is that you need to align these objects. So before, when we've been doing this, we've been aligning all of these objects, okay? And what I'm telling you here is think about doing the following. Take an object, put it in over the direction. Directions from this distribution, and you get a collection of Euler characteristic curves, or you're going to get a collection of diagrams, right? I think so what we're saying is that then do this for another object. Okay. Now, if you can measure the distance between these two distributions, you can measure distances between objects willing to align them. Assume general constraint the objects. Right? Now, it is true that measuring these distances between these distributions isn't absolutely trivial. Measuring distances between distributions of curves is not that bad. I mean, there has been previous work done in statistics on this. So we're doing this. So this is the idea that maybe you can measure distances between these objects without having to align them, which could be very helpful in many cases. So that we've worked out. And let's show you some results. Okay, so here's data from 106 primates, and this is taking the Euler. No, this is taking the persistent homology transform and taking the distances between these 106 heel bones, and using multidimensional scaling to scale it down to 2 dimensions. And you start seeing at the kind of at the top right, you see great apes, and in the middle you see old world monkeys. And I think so is actually an extinct old monkey. Going down, howler, squirrel monkey, new world monkeys. If you look at kind of going towards the left, those are all lemurs. So it's starting at what you the kind of called taxonomy. And if you look better, this is what it looks like. If you want to put in the phonetic clustering and what you kind of are. And let me actually show you 2 things. So here, if we compared methods, the persistent homology method with a mid-place landmark data method. This is kind of classic shape statistics approach, and then an automated landmark approach, which Doug, Ingrid, and I and others have been working on. Quantitatively, the persistent homology one looks better, but again, it could be very interesting to use other types of summaries and to investigate this in more depth and really get a better feeling for what's going on. And my colleague Doug said that one of the ways that the persistent homology was better is that the hylobates look like other apes, and before they look like alouata. And then later what that means is that in this case, the hylobates, which just look like apes, and previously I think the gibbon looked like howler monkeys. So this was good. Now, is with graphs. So right now doing this shapes. Can we do this with graphs? So you can think about taking a graph, compute the graph Laplacian, the vertices of the graph using the graph Laplacian, the eigenvector of a graph Laplacian, and just like a direction. And you can compute, for example, the Euler characteristic curve. You can do the various directions and you can measure distances. In far right, I'm looking at perturbations of the blue, and these are distances between them. And on the further right is perturbations of the red graph and distances between them. So we're seeing how far this can be done. Clearly, it's not going to be a sufficient statistic here, because otherwise we would have solved the graph isomorphism problem, which I'm sure I haven't. But I think exploring these type of objects is very interesting. And the reasons why, and one of the things that's motivating me in doing this is I want to do kind of classical idea statistical genetics and quantitative genetics on traits that are shapes. So I want to say, answer questions like, give you a bunch of bones. how much variation of in the heritable and how much of it is environmental, right? Or if I give you a bunch of, for example, these brains development in a fish, in stickleback. If I see these images and I give you the phenotype data from these fish, can you tell me which loci are most explaining the variation there? So doing association studies. So we're very interested in things like that. And another example of this is trying to model variation in the microbiome networks of these baboons, which I alluded to earlier. So again, that's another area where we're trying to use this. Now, before I spit about stochastic topology, I'll do that fast. I think there's a lot to do with kind of Euler integration setting questions like how many directions do you need, right? If you think we do localized transforms, so instead of sweeping through the entire object, can we sweep through part of the object, right? So can something a little bit more local. You can almost think of this as a signal processing question on for shapes and surfaces, and maybe going on in terms of networks for people who've thought about dictionary learning in statistics. Is there a way of doing dictionary learning with these summaries? So I think there are a lot of really open, interesting kind of problems here. And I'll just close with some ideas on, actually, Peter, should I talk about the stochastic topology, or should I just stop and take questions?
If you want.
Okay. So I'll kind of just go through this here quickly, okay? So this is a problem statement. I have endpoints from a distribution. The support of the distribution is on a manifold. Think of a torus, okay? Looking at is the union of epsilon balls around these endpoints, okay? And to say something like, if I have enough points, the homology of this ball is equal to the homology of the manifold, let's say. So that's a kind of that's a problem statement, and this was a problem that was solved and addressed in a paper by Nyogi, Neil, and Weinberger, and it was one of the papers that kind of started really asking questions about both randomness and inference, formal statistical learning in topology. And there are other ways of thinking about this, and about this randomness in the Euclidean setting. There's been done work by Matt Kill and then Omer and Robert on random geometric complexes, limit theorem for Betty numbers, and then in a manifold setting, the paper I just talked about, finding the homology of some manifolds with high confidence. So key ideas in a lot of this work is if you take these unions of these balls, and if you look at check complex, something that you say about the unions of the balls or the check complex is equivalent to the check complex. That's kind of a key in a lot of full way. Try to prove theorems is try to make statements about the check complex and basically look at the duration of balls and try to make statements about certain functions or certain events happening on them. Is the way the general proofs in this area goes through. Now here, and this is a lot of the work that Omer Bobrowski's been doing, is if I object and let's say it's embedded, it's in a manifold, the dimension of the manifold is D, the dimension of the ambient space is capital D. There are three regimes. One is as I scale the number of points n, and the radius, right, the D is going to 0. Another one, it goes to a constant, and the other one, it goes to infinity. And these can be separated out as critical, subcritical, critical, and supercritical. And you get different types of phenomena in each of these. Okay, and you can think of n to the RD as the expected number of points in a ball of radius R. And so if you first look at the subcritical, you can ask what is the limiting mean of both the numbers, which is the top line. You can also characterize this for the number of critical points, and then look at what they look like, and you can basically come up with a combinatorial argument, and formula for these. Do more variances and give statements about convergence as other critical points for the values. So again, in case you can do that. Now, the point here in subcritical regime, which I think Omer calls the dust regime, you basically have this case where nothing's very well connected, not very well connected at all. And so the beta is going to be dominating Betty number, Betty 2, so on and so forth. And basically, the number of connected components is going to be of the order of the number of points. And you can have a critical radius, which is telling you how things change. So as a picture of that is as the radius gets bigger and bigger, it's a lot of things, right? Of Betty, and it gets a little bit bigger, and then you only see Betty 2, but fewer of them, still infinite, and then so on and so forth. You can start characterizing this. And what happens in the critical region? In the critical region, so you can again start saying things, and you can say qualitatively about the Betty numbers, but make it and still say things quantitatively about the number of critical points. Why we have a hard time saying things more qualitatively about the Betty numbers is that combinatorics becomes very hard, and is more technical, but the combinatorics become harder. Now we can still say certain things. We can say things about the Euler characteristic, because then the alternating sum of the Betty numbers is related to the alternating sum of the points. So we can say something about that, but it's again hard for us to say something about the Betty numbers themselves. We can again be quantitative only about the critical points. And this is the supercritical regime. So here everything is highly connected. It's almost covered. We again can give you quantitative results about the critical numbers. We can give you limiting distributions for variance and means, but we have no general results for the Betty numbers. And we can do a little bit more. We can give you the probability of vacancy, basically the probability that there's still a hole, with the probability that there's a coverage. And what we can, so we give you a radius r, which is related to this coverage threshold, for which we can tell you that the Betty of this union of the balls is equal to the Betty numbers of the manifold. And it comes back to saying that the homology is equivalent. I'd also be very interested in characterizing at what level r we can make this statement in probability for like dimension 1, then dimension 2, then dimension 3, and kind of. And this is kind of the work that I've done with many, many, many people. And I'll stop there, and I guess we'll leave time for questions.
Thanks a lot. Earlier talk, you talked about statistical inference on topological summaries, and you talked about like using Babel to calculate things. Can you say something about the priors for statistical inference for?
Yeah. So in the example that I gave, that So in the example that I gave, the prior is really simple. Okay, it's your prior probability of having one object versus other. So that's trivial. Okay. Now, if you want to do Bayes' rule, right, and if you want to use prior on summaries, then that gets on topological summaries. That gets a bit trickier. So one question is, how can you put a prior on configurations of persistence diagrams? Right? You can think about point processes to do this, and I know people who are. So that's one approach. There are other approaches. Another you can do is you can think about what Peter's been working on with persistent landscapes, and you can think about, well, how do we put a prior on persistent landscapes? And that can again be done because persistent landscapes, in a way, are, you can look at those, and if you look at them, they look really like splines. They're like a kind of splines. We have ways of putting priors on splines, right? So I think, there's things that can be done there that I think are really useful. Now, that we don't know how to do very well, and we need to better understand before we go and often start putting priors on diagrams, is we have an idea of what likelihoods mean in these summary spaces, right? Likelihoods shouldn't just mean that things that are closer to the diagram are noise or more, unlikely. You need to have a better idea of, some data generation process, right? We have a process that generates point clouds that we can actually think about the likelihood of. We can say what's the probability of generating these process, and then look at the map of that onto persistence diagrams or landscapes, or whatever you like. And then some indication as to, what that looks like. So what would be a reasonable likelihood model in diagram space? We've done very little of that. I think we're starting to do things like that, but I think that can possibly be quite useful. We same thing for summaries, and for many models, we don't necessarily like let's say if you're doing statistics and what you're looking at is a jump process, right? This jumping. One summary could be you just look at the number of jumps above size D. People who studied Levy processes know the distribution on the jump process is related to the distribution of the counts of jumps over size D. And these map, and so they can think about how this works. So that type of thinking, I think we're just starting to do.
I'm interested in with this homology transform or the Euler characteristic curve version of it. If you take all the directions, then you get a sufficient statistic. And you said something about taking just a few of them. Say more about that. I mean, so what if you only had a certain number of them? Could you say anything about how much you can recover, or what's the nature of this moduli space thing?
Right. We're trying to understand that right now. So we're very interested in and there are various ways of thinking about that. That you can think of, as you said, the nature of this moduli space. You can think of it as a sampling theory for surfaces. You can also think of it as a way of characterizing how complex a shape or a surface is in terms of how many directions do you need. For this family of surfaces, you need X number of directions before you capture all of this. And this is something we are working on. I've talked to Ali Barishnikov about this, and I have been thinking about it. And there may be ways of adapting that have been done in the radon transform literature to do this. But I think it's open, and I think it's very, very interesting. So going back to if you think of all of these things as some form of Euler integration, right? Then what do you have? You have basis functions. One way is a basis function is going out and it's looking at the sublevel sets, right? But then we could have basis functions that are going out and localized and they're only going at parts of sublevel sets. And you can ask questions about, for all these different types of bases, right? Do we get better or worse? Could look at more and more of these bases. Right? And is it true that for certain families, certain types of bases are better? Right? If you want to think about it from an Euler integration perspective, and then I think that's extremely open. So yeah, truth, measuring distances between shapes. Shapes are not isomorphic. I'm not quite clear. No, truth. So
I have a quick question.
Yes.
We're doing when you think that there might be potential shape comparison without alignment.
Yes.
Would you elaborate a little bit more, because it seems a little bit counterintuitive that some form of alignment, even alignment through directions, have to be in place before any sort of comparison could be possible.
Okay. So let me talk about this a little bit more. Let's say, for example, the shapes have been aligned in terms of at least scale. Okay? The following thing. I took a shape, right? I took all of its directions. Okay? And I got the Euler characteristic curve. Okay? I take the shape, I rotate it randomly, and look at the Euler characteristic curves. Okay? Now, if I label the labels, or just say all of the labels, okay? If you could align these two distributions, the distance would be 0. Would you believe me there? Symmetries. So basically, all we're doing is we're generalizing that observation. Now, the question is, in terms of only practical, right? If you can cleanly measure distances between these distributions, right? Directions such that you can get remeasures between these distributions. So kind of it seems a little counterintuitive, but I'm not sure that it is, because if you have something and it does have some set of symmetries, right? Take enough directions, I should to figure out what the distribution over the directions look like.
Sorry to butt in, but I think an important point to point out here is that as you change the directions, the Euler characteristic curves or system diagrams change in a continuous way.
Yeah.
So what you're really looking at is the image of the sphere in the space. And if your shape doesn't have too many symmetry, then you're going to get this injective embedding of S2 into your space. So really just compare images of these S2s, which correspond to the directions within your diagram space or Euler characteristic curve space.
Basically, like if this is the intuition, then that means the complexity of the shape, the sort of, in lack of better words, the correction among all those distributions will become complex as well.
Yes, you may want to use an Earth mover's distance or something, and then it wouldn't really matter too much if you had to take more directions.
Thanks.
Do we have? All right, let's all thank Sayan on a great talk. Thanks a lot.